Alright, on the last tape we left off with the cross-shearing stress in a beam. We know shear, we know moment of inertia, we can figure out how thick something is. This is the guy who's going to give us a little trouble, without a doubt. It's the first moment of area above the level where the shear stress is desired. Now, just to show you what you will see in your book, this is the shear stress, and this is what they call shear flow. All it is takes the B out. It's shear flow. Pretty much the same thing. Here's a pretty good reminder of what Q is. Q is some area times how far is it. This will be the only jogging of your memory you're going to have, even after I show you how to do it. The area under discussion is the area above the layer upon which the desired shear stress acts, and Y is the distance to the neutral axis from that centroid of that area. Show you some examples. First, I want to make sure that you really know how these stresses are distributed. As I showed you earlier, the stresses arise because of an imbalance in the moments. Because this moment was a little puller to the left, because this moment caused some big pulling to the right, there was an imbalance which caused some big shearing stresses at the neutral axis. Interestingly, if the guy would cut his free body right about here, just a short distance above the bottom, then what you would see is some even smaller, because you cut off less area, you didn't do this, and this one isn't too much bigger, it's just a little bit bigger. And the reason is all of this imbalance here is no longer on the free body. These two imbalances no longer are in effect, and only this little imbalance is in effect. So on that face lower down here, you would see much smaller stresses than you see at the neutral axis. Hence, here is the end view of a beam. You'll notice that the maximum shearing stress occurs at the neutral axis. This is the end view. And it tapers off parabolically till it gets to zero. There's no shear stress on the top or bottom of a beam. Now, for a wide flange, the shearing stress is still distributed parabolically. It's still a maximum at the neutral axis, but right in this region right here, when you divide by the thickness of the beam, you're dividing by T. Divide by T, divide by T, divide by T. Now all of a sudden you divide by 30T. Probably 30 times wider up there than it was there. Therefore, the stress drops off dramatically and continues on its parabolic way. On a T-beam, the neutral axis is here. You'll notice the maximum shearing stress still occurs at the neutral axis, but once we get into this thick section, the stress drops off and continues parabolically. Those are distributed parabolically. If I could show you those, here would be this rectangular beam right here. You'd see great big shearing stresses at the neutral axis. You'd see pretty good shearing stresses a quarter of the way. You'd see no shearing stresses at all at the top. And then again, some medium-sized ones down here and some little tiny ones at the bottom. They'll be distributed parabolically, like that. Now then, let's get a Q value. I'm going to tell you that I have a rectangle, and that rectangle is 10 or 100 centimeters tall, and it is 60 centimeters wide. And I don't know why, but my boss asked me to determine the shearing stress on this line, which was, if that's 50, that looks like about 30 centimeters above the neutral axis. And I guess maybe what he's going to do, I'm going to buy a couple pieces of wood, glue them together. He wants to know how strong the glue needs to be. That would be a good reason to determine the shear stress, because glue would have to hold that shear stress. Now here's the rule. This is what you do. To determine Q, first you put your finger on the neutral axis. Then you go to the line where your boss asked you to find the stress. Then you crosshatch everything above that line. That is what your notes call A prime. Here is the centroid of the crosshatched area, and it is this far from the neutral axis. Now, since this is 30, then this is 20. And since that's 20, this is 10. And so the distance from the centroid of the crosshatched area to the neutral axis is 40. That's what your notes call Y bar. So it would be A prime Y bar. A prime would be 20 centimeters deep. It would be 60 centimeters wide. And how far it is away from the neutral axis would be 40 centimeters. And that's Q.
48,000.
48,000 cubic centimeters. Now I might go back to the boss and say, you know, you'll find some bigger shearing stresses right in here. He'll say, are you sure? I say, yeah. Big shearing stresses live on the neutral axis. He says, how big? I would go and put my finger on the neutral axis. I would crosshatch everything above that line. And you know, who's to say what's above? Down is just as good as up. You crosshatch everything on one side of that line. Just usually makes the numbers easier if you crosshatch, you know, out away from the neutral axis. Q for the neutral axis is equal to, the crosshatched area is 50 centimeters deep. It is 60 centimeters wide. Here is the centroid of the crosshatched area. That's half of 50. 25 centimeters is equal to
75,000.
And that's how come the shearing stress is bigger, because Q is bigger. The shear acting on the face is the same no matter what. The Q changes. The moment of inertia is the moment of inertia about the neutral axis. Every now and then you get somebody trying to take the moment of inertia of the crosshatched piece. Not so. The moment of inertia, neutral axis moment of inertia, is the only one you ever use for any computations. And then the thickness would be 60. And your notes don't use T for thickness, he uses B for thickness. So if, I don't know if there is or not, but if there were 5,000 newtons acting on that face from my shear diagram, times 48,000 centimeters cubed, divided by the moment of inertia of that thing. Well, the moment of inertia is, it's nothing but a rectangle. So its base times its height cubed over 12, there would be his moment of inertia. And then how thick is he? Well, He is at the boss's request location. He is 60 centimeters wide. And that'll tell you the stress in newtons per square centimeter. There's a centimeter here, and there's 3 more of them here. That'd be newtons per square centimeter. If you want it in Pascal, you got to change it to newtons per square meter. Alright, let's try this one here. We already did one like this. Here's a T-beam. My boss intends to glue these 2 pieces together right here, and therefore he wants to know the shear stress right there. Now theoretically, the stress right above that line, you'll have to use this for B. And immediately below that line, you'll have to use this for B. Obviously the glue is only going to fit on this piece, so I would only calculate the stress below the line, not above the line. Here's Q. Put my finger on the neutral axis. Done so. Go to the line where the boss wants the answer. Done so. Crosshatch everything on the outside of that line. Done so. Spot the centroid of that piece, and Q is equal to the crosshatched area times where is it with respect to the neutral axis. Its area is 6 inches by 2 inches by the distance from here to here is 5. Let's see, the total is 8. Take away 5, take away 1. In other words, put your fingers at the top and the bottom. That's 8. Take away 5 to get to the neutral axis. That's 3. Take away 1 to get to the centroid. That's 2. 2 inches. So 6 inches, 12, 24 cubic inches. If you would like to know the shearing stress at the neutral axis, it will be a bigger number because Q will be bigger. You could do it like this. Q would equal to 6 times 2 times 2. That's the same Q we had before. Plus the little piece in the middle now is 1 inch deep. He is 2 inches wide, and he's a ½ inch up. So there's Q for the neutral axis. You won't find a bigger Q than that. 25. Another way to do it is to put your line on the neutral axis, go to the place where the boss wants the answer, and crosshatch the area. Q is equal to 2 inches wide, 5 inches deep. 5, half of that's 2 1/2. 25 inches. Same answer we got before. Now there's one that could probably take you all day to find Q and I if you break it up like he's hinting for you to in 4 pieces. Here's the quick way. I about the neutral axis. We know the neutral axis is in the center due to symmetry. The neutral axis is equal to the top is 10 across. The whole solid thing is 14 deep. BH cubed over 12. But you say you forgot the piece in the middle. Minus 10 times, that's the base, it'd be 6 times the height is 10 cubed over 12. Now since the centroid of the solid pretend piece is right in the middle, he gets no transfer. Since the centroid of the missing piece is right in the middle, he gets no transfer, and that's the end of it. That's the moment of inertia.
1787.
1,787 inches raised to the fourth power. Here is Q for the neutral axis. Q for the neutral axis is equal to 10 wide, 5, 6, 7 deep. That's this piece right here. 10 wide by 7 deep times 3.5. That's halfway up the 7. But I lied. I took into account this piece, which is 5 wide, 5 deep, and 6 wide. It doesn't matter if I reverse those. Times 2.5. Because his center is in the middle, up halfway up a 5. His Q is
170.
170. I'm sorry?
170.
170 inches cubed. If you'd like to know this guy's Q for the top, it's equal to, put your hand on the neutral axis, go to where the boss wants the shear stress, crosshatch everything above that line, put it centroid. Q is equal to 10 wide, 2 deep. The distance to the centroid is 5 plus 1, that's 6. So 60 times 2 is 120. Incidentally, T for that top piece, how thick it is, excuse me, B, your notes call it, this is B. B starts here and stops here, and then starts again there and stops there, so B is 4 inches thick. That thing is 4 inches thick. Just below the glue line. Alright. There's the beam that has 4,000 pounds of load on it, a moment of inertia of 895. All I've been asked to do is find the shear stress at that interface and the shear stress at the neutral axis. Q for line AA is equal to 8 times 2 times 5, how easy?
80.
80 inches cubed. How thick is line AA? It's 2 inches thick. Excuse me. B. Half the books use B and half of them use T. I'm used to using T. Shear stress. V. Q. I. B. But notice the units come out inches to the 5th on the bottom, inches cubed on the top. That gives you pounds per square inch.
179.
179 pounds per square inch of shearing, wiping stress. That's on line AA. Here's the shearing stress at the neutral axis. 4,000, same load. 895, same moment of inertia. Still happens to be 2 inches thick. And here is the Q. 80, that was the previous number we had, plus we have another piece. This new piece is 4 inches deep, it is 2 inches thick, and its centroid is 2 inches from here to there. And whatever that works out, should come out bigger than 179.
215.
250. All right. Now, The next thing we do is deflections of beams. By deflection, I'm saying if you have a beam that holds a load, when you put the load on the end of it, like a diving board, it deflects. You probably don't see much of that except a diving board, because we design structures so that they do not deflect large amounts like that. You're used to it happening to you on a diving board, but if it happened to you in a room, it still might be perfectly safe, but it'd scare you to death. So these numbers are reasonably small, and they're limited by code how big they can be too. Now there's two ways that you can solve for how far this beam moves down as you apply the load. There's a bunch of ways, but the only two that you care about is direct integration and using tables. The reason I say they're the only two you really care about, unless you know some others and are very familiar with them, those are the two that you more than likely use. Now the reference manual gives you equations for deflections of beams. This isn't really deflections of beams, this is going the other way. This is saying that you could take the differential of your moment equation, you get the shear equation. You could take the differential of your shear equation and get the load equation. We've been working from load to shear to moment. That's normally the way you go. But you can go from the moment diagram, if you have your equation in moment form, you can integrate it and go to the slope and find the slope diagram. And then you can integrate the slope, which is a double integral of the moment, and you can find out how far something moves. As you do that, you pick up constants of integration, which you'll have to work out from how the beam is tied down. Here's a brief example. With any luck, they'll give you a case that you can solve using the tables, but who knows. In this one, there is a cantilever beam. It's fixed on the right-hand side of the wall. It has W pounds per foot of load on it. We have arbitrarily chosen this as our origin, and we call that the distance x. That means that the bending moment at any point, right here for instance, can be found by drawing just a little piece of the beam, putting that load on it. This length is L minus X. That's how much of the beam we arbitrarily cut off to study. So the load is W, that's the height, times the base is L minus X, that's the load. If you want to know how much moment there is, you multiply the load times the distance to the centroid. Well, that would be another L minus X over 2 to get to the centroid. So there's your bending moment. The reason he's doing that is in order to use this integration technique, he has to have the moment in equation form. So here you see, same thing we did, and he works it out and it gets minus W over 2 times L minus X squared. The reason he puts a minus on it is because the beam is going down in the shape of a frown, therefore it's a negative moment, and so he just brings the minus sign along with it. Now then, to get the first integral, he merely integrates the L minus X. The W over 2 is a constant, he just brings it out. So he integrates L minus X squared dx, which gives him L squared X minus L X squared plus X cubed over 3. That's the integral of this term. It's expanded. And you notice he picks up an arbitrary constant. Now to get rid of that, he has to know something. And he says, you know what? I know that when X is 0, the shear is 0. happened there, we had a little discussion. It's symbology. You look at this and you think he's talking about the shear. You're not talking about the shear. He's talking about the slope of the beam. In your notes, he calls the slope of the beam, well, he doesn't use a symbol for it, he just says dy dx. If you integrate the moment equation, you get dy dx. That's probably a better symbol for this. But dy dx is equal to 0. What he's saying is this beam is like a diving board. It's going to come out like that. It's going to have no slope at x equals 0 because it comes straight out of the wall. So there he says dy dx equals 0, which is what you got by this integration. Therefore, if you put x equals 0, x equals 0, x equals 0, I don't care what the load is, and C1 will be equal to 0. So EI times dy dx. This is an equation for the slope of the beam at all points. Now you can find the deflection of the beam by integrating the slope. So he brings the W over 2 constant out. He integrates L squared x minus this stuff. So here x goes to a 2 power, x goes to a 3 power, x goes to a 4 power. That makes sense. Plus he picks up another constant. However, the beam does not move up and down at the wall. In other words, the beam did not deflect. So he can put 0 here, 0 here, 0 here, and find that C prime is 0. So then all he has to do is plug into this equation for y. Y is equal to minus W over 2EI, that's this one, times this thing, plus there isn't any constant. So now he's got an equation for the deflection at any point on the beam. Now, the question was, give me the greatest slope and deflection. So all you got to do is go to your slope equation and plug in x equals L. And go to your deflection equation and plug in x equals L. And you'll have the maximum deflections and dy dx. So that's by integration. It's obviously not a lot of fun, not something you do if you could get out of it. And a lot of times you can get out of it. These are in your book on page 33. And they are deflection equations. For instance, if you have a beam which is fixed on the left-hand end or on the right-hand end, they probably turn it around backwards to see if they can mess you up. But if it's fixed on one end, then you call A the distance to the load and B the free end that sticks out. He'll tell you how much rotation this beam has. That'll be theta max or phi max. He'll also tell you the maximum movement up and down. And he gives you those equations for deflections. I don't have enough of the sheet there when I blew it up. Yes, this one says for x greater than A, and this is for x less than A. The other things, when I said I'd give you delta max, your delta maxes are over here further down in the sheet. And also the maximum slope of the beam. So now that would be for cantilever beam. Here's for a cantilever beam with a uniform load on it. Here's for a cantilever beam with a concentrated moment on the end of it. Here's for a simply supported beam with a load not in the middle. And then there's a couple more that he gives you. Now, if possible, what you want to do is you want to piece together cases that will let you do the problem without having to integrate something like this. So, for example, if the problem was, tell me how far this beam with a uniform load on it, and maybe this is 6 feet, maybe this is 10 feet, maybe this was 2 kips per foot, something like that. How far does it move down? Well, you look on page 33, there's not one of those. But what you could do is you could find out, don't know why I drew that line, because that downward load obviously isn't going to push up. You could find out how far a cantilever beam pushes down when you load it across the whole thing, even though you don't want this piece right here. And this isn't quite the right answer, but it's better than nothing. And if the answer came out 1.2 inches, and the possible answers on the quiz are 1.3 inches, 2.8 inches, 4.9 inches, and 6.3, well, then I'm pretty sure that this is the answer. Because when I take this load, now let's see, I might have to put something else here, say 1.1. Because if you take this little piece off, the thing ought to back off a little, and there aren't any other choices any smaller than this one. However, you can still get it, because what you do is you merely add this case right here. You add another beam with the load pushing up and put 2 kips per foot on it, and that means that this 2 kips per foot that you put on here you didn't want, you canceled it with this here. Now that beam will move up, and it will also have a slope to it. And you can find how far a beam moves up with a uniform load on it. And you can also find this slope, so you can take away how far the beam itself moves up, and then knowing the slope, you take off this much more, and you'll have this case. So what you really are going to do is piece together, cobble together an answer out of the stock sets of answers that he has. All right. Cylindrical pressure vessels. Cylindrical pressure vessels have hoop stresses in them. I'll show you what those look like in a minute. They act around the tank in tension. They have long ways or axial stresses, longitudinal stresses. The equations are given in your reference manual. And they have a maximum shear stress of PD over 4T. The hoop stresses are the biggest. You'll notice it's only divided by 2, whereas the longitudinal stresses are divided by 4. Here is a picture of what a half a tank looks like. You'll notice it has hoop stresses. The hoop stresses are running like in the hoop direction. They called them hoop stresses because they used to make these things out of barrel staves. They put beer in them, and they had to put steel bands around them. They had to put hoops around them to hold the barrel together. And that stress is exerted on this wall of the tank because of this internal pressure. And this hoop stress is equal to P, that's the internal pressure, times D, the diameter of the tank. Take the mean diameter as good as anything, or take the inside, take the outside, doesn't much matter. And divided by 2 times how thick is the wall. Now there's some long wave stresses in the tank also, longitudinal stresses, and they're given by the equation PD over 4. They're actually only half as big. So if you ever put pressure in a tank, it almost always blows up this way as opposed to blowing up the 2 ends coming apart this way. Stresses are only half as big. A spherical pressure vessel has the same stresses in all directions, and they're the same as the longitudinal stresses in the other one. Maximum shear stress in that one is PD over 4T. That's correct, but that I changed to R here. That's a mistake. Really should say PD over 4T to be consistent with the other one. This ought to say PD over 8T. Is that right? Well, here they are. Yeah. Probably won't have a spherical tank on there anyway. He doesn't give you the equations. So this is your reference manual, same equation. And here's the axial tension, there's the hoop tension. With everything defined. Now we could work one of those right quick. Here's a tank. It is 60 inches big. Got an internal pressure of 100 psi. Has a wall thickness of 0.5 inches. It is 200 inches long. Length means absolutely nothing, but it'll probably be one of the wrong answers on the quiz if you accidentally put that in instead of this. And therefore, the hoop stress in this direction is PD over 2T. Pressure is 100 psi. Diameter is 60 inches. Inside diameter, yeah. Outside diameter, yeah. Mean diameter, yeah. Divided by 2 times how thick is the wall, 1/2 inch. And those the units come out. PSI, stress, that's good. Equals whatever it's equal to. Alright, now we go to columns. The equation for the critical buckling load. This is a death load. This isn't an allowed load now. In other words, the thing is guaranteed to pop out to the side at this load. It's derived, and a rather lengthy derivation it is, it's derived for a pinned column that simply kicks out to the side. Because that's one of the more standard columns. If you don't like that column, if yours is connected on the ends differently, we make adjustments. How much load you could put on that column on both ends is given by pi squared. You know what E is. I is the moment of inertia. And L is the length of the column. If you don't have a pin column, that's what the K is for. The K takes into account and it turns the true length into an effective length. Now, some columns act as beams, but they're pretty short. Only if you're not going to buckle this thing. If it's a relatively fat beam and it's got a column load on it and it's also bent, in that case, here's your P over A stress that you've learned earlier. That's due to your axial load. Here's your MC over I stress. That's because the beam is being bent. You simply add those two stresses together. On one side, you'll have compression due to the axial load. In this beam right here, you'd also have compression on the top. So the maximum stress on the top would be, tell me that part from what you already know. Tell me that part from what you know how to do. On the bottom, you'd have compression due to the axial load, but you'd have tension due to the bending. So that would be F over A minus MC over I. Now, back to column Here's what your book gives you. Here's his beam columns. This is called Euler's formula. You need to know when he says the word long, he means long. This might say, this one's for short columns. So if he asks you, when should you use that? Can you use it on a long column? The answer is no. If he says, what's this good for? You say, well, long columns only. Now then, this equation that we just got can also substitute what a radius of gyration is. The radius of gyration is defined as that distance where all the area could be placed when squared gives you the same old moment of inertia you previously had. And it's handy sometimes to use the radius of gyration instead of I in this equation. So the equation looks like this. Now this is not a critical load now, this would be a critical stress. Because he's divided by area. He took the area over to the other side. Alright, here are some typical K values. If you like a theory column, then use these numbers here. If you like a real column in the real world for design purposes, use these numbers here. So he'll tell you which he wants. You want a A&M number, or do you want a real building number? This is theoretically exact. The problem is they find you can't really both ends fix very easily. It's very difficult to do. Since there's always a little looseness in it, this K is not as advantageous as you think. The lower this number is, the more load the column appears to hold. So, here's an example. Here is a column which is going to have a load on top of it, P critical. This particular column is like a 2x4, except a European made it. It's 50 centimeters thick and 150 centimeters wide. Stands up in the air 5 meters. It's solid. It's made out of aluminum. I got this 6.9 times 10 to the 6 pascals, which is 6.9 times 10 to the 10th newtons per square meter, right out of your book. I'm telling you that I don't want a theoretical number. I want to really go build it. And so I want to know how much really will cause failure. So use design K values. Now the problem is, if you'll notice the way he's got it, he's got the darn thing wired up. Now what that means is the column could buckle about its strong axis. In other words, it could buckle to the right like this. And it wouldn't even know the wires are there. The wires would just go with it. So the wires are ineffective in supporting the top about the strong axis. So I'm going to see how strong this column is about its strong axis, assuming it is a fixed, free column. If it was pin-pinned, I had to use pin-pinned numbers. Now I went ahead and calculated the moment of inertia. And let me make sure we know why these numbers are like this. If you say it's going to buckle about the strong axis, then I'm going to show you that as the buckling axis. I'm going to show you a lot of material way off of the neutral axis. I want to show you the base is 50 and the height is 150. That would buckle about the x axis. If you think it'll buckle about the x axis, I don't care if it's strong or weak. If you think it'll buckle about the x axis, then you show x horizontal, and that's the base. So the moment of inertia is base height cubed over 12. That comes out 14.06 times 10 to the minus 6 meters to the 4th. You notice I changed my centimeters to meters. Also, if you will look in your reference manual on page 32, you will find that one end fixed and other end free design value K is 2.1. Theoretically it's 2, but design is 2.1. Then I simply go to my equation, which says P critical is equal to pi squared EI divided by KL squared. So that's pi squared. E is 6.9 times 10 to the 10th newtons per square meter. Moment of inertia is 14.06 times 10 to the minus 6 meters to the 4th. The whole mess is divided by 2.1 times the true length, 5 meters, and then squared. So to buckle about the strong axis, we'll take a load of
86,850.
86,850 newtons of force. Probably be better to say 86 kilonewtons. Alright. The problem is it might not buckle about the weak axis. It might buckle about the strong axis. I'm not sure I'm going to draw that. But let me show it. Let me show it flopping in out of the paper like that. They both look very much the same, but this one bent in the plane of the paper and could not come in and out of the paper because of the wires. Now I'm assuming, oops, it can't do this either, can it? See, this piece can't come out like that because the wire will stop it. What it has to do is it has to come out like this. It has to come out like that. It has to be fixed at the base, and it's just like it has a pin at the top about the weak axis because these wires pin it about the weak axis. So that K, if you look in your book, is for one end fixed and the other end wired or pinned. That's where I got the 0.8. Now the moment of inertia, if it's going to buckle about the weak axis, I show it like that. Now the base is 1.5 and the height is 0.05 for a moment of inertia. There's the K. And now P critical is equal to pi squared E 6.9 times 10 to the 10th I 1.56 times 10 to the minus 6th divided by 0.8 times the true length squared. How much?
598,430.
598,430. Now we're not guaranteeing these numbers. If you crank them out, you may get something else. But if that's right, if we hadn't made a mistake somewhere here, then it will buckle about the strong axis. In other words, the wire prevents it from buckling about its weak axis, so they did help. They're worth the money. But now it buckles about the strong axis. All right, combined stresses. Many times you have both axial loads and twisting on something. For instance, here's a bar that is being stretched. Let me show you a small postage stamp here. You would have to show me some tensile stresses on that postage stamp because you stretched the bar. Then let me twist the bar with a torque T. That's going to cause some shearing stresses like that.
Since this torque went up, when he finally gets over to this little postage stamp at A, he'll scrape up on the right-hand side. To keep the postage stamp from moving up, somebody's going to have to pull down on it. Actually, there's another pair of arrows that go to keep the little block from spinning. You see, those two arrows make it want to spin counterclockwise. So another pair are generated internally that stop that. They are equal in magnitude. Now then, you could have axial and bending. You could have stresses under footings. You could have axial, torsional, bending, and pressure. Wow. And then there are equations to tell you how to handle those stresses. For example, here's a case that I just showed you. It has a load on it and a torsion. You would have to draw a little postage stamp on the side of the block and do nothing but this and show me what he did to the postage stamp. Here's what he does to postage stamps. That's what he does. Then you have to draw me the same postage stamp and put on there nothing but the twisting. Well, the twist comes around and he comes around and he comes around. You remember how torque calls shear? He causes a shearing stress like that. To put that in equilibrium, one on this side will appear. To keep these two from going counterclockwise, these two will appear. And the total sum of what's happening to block A will be the sum of these. Here's one that's bent due to a tension load, but he put it off center. By moving it off center a distance E, in effect, he has this, but he also adds this, a bending moment M of magnitude load times eccentricity, since the load is off of there. So you'd have a little postage stamp, say, on the bottom, which has pure tension on it, P over A because of this guy, but then you'd have some tension on the bottom of this one, same postage stamp. The equation is MC over I. The final answer would be the sum of these. Alright, now let's skip that. How many minutes we got? 8. Alright. Every now and then, you will find a little block that has some stretching in the X direction. It's probably because of maybe some P over A. I don't know who caused it. You also have the possibility of some sigma Y stresses. I don't know who caused it. Maybe hoop stress caused it. You may also have some shear stresses acting on the little block. I don't know who caused them. Some tau stresses. Maybe twisting torque caused them. But knowing the magnitude of those three stresses, you can use equations called stress transformation equations from statics, and you can find the stresses on any plane the boss wants you to. If he wants to find the stresses 30 degrees away from the vertical face, the stress transformation equations will let you do it. Also, it'll let you find the stresses, the principal stresses, the biggest stresses. The sad part about this situation is if sigma x is 2 and sigma y is 3 and tau is 4, the biggest sigma stress down in here is probably 5. It's bigger than anything you see, and it's hiding. Same way with the shear stress. Inside there, at some other plane, I don't know where, there is a bigger stress than 4. That's what the equations do for you. If he asks you for the stress on any plane, you pretty much got it made. Because if you know sigma x is 3 and you know sigma y is 5, and you know the shearing stress right here is 7. If that one's 7, this one's also 7. There's 7 all the way around. Then you can find the shearing stresses on any new plane of your choice. Merely tell us how far these faces rotated from the vertical to the plane, or how far this rotated from this axis, and you just plug in. Put sigma x there. Here, let me do something right quick. Let me put sigma x like this is 3. Let me say sigma y, maybe wasn't attention. It went this way, and sigma y was 5 compression. And here the shear stresses didn't go the way that you see them in the diagram. They actually went the other way, and they're 7. Here would be sigma x on the 30-degree plane. Sigma x prime on the 30-degree plane is equal to sigma x plus sigma y. Look at that. The reason is because your sigma x didn't agree with your sigma y didn't agree with my sign convention. My sign convention for these equations is very rigidly fixed. Tension, tension, shear in the direction shown on the block. Not this way here just because it happens to be your case. So I have to put a minus 7 divided by 2 plus sigma x minus sigma y over 2 times the cosine of 60 degrees, 2 theta, plus, now the tau is 7, but it's going the wrong way, so I got to put a minus 7, times the sine of 60 degrees. That would be the stress, this guy right here. You could also find the stress in the y direction. I don't even think it's shown, but it actually, you'd have to cut the block again to see it. And you can find the wiping stress, shear stress. But most times, you'll probably have a block that looks like this. Rather than being asked what is the shear on the 30-degree plane, they'll want to know the biggest stresses. Let's just say that the stress in the x direction is 3, the stress in the y direction is 5, and the shear stress is 7. If that's 3, that's 3. If that's 5, that's 5. If that's 7, that's 7. If those go clockwise, these go counterclockwise. Now there is, what happens is these equations that we looked at a minute ago, turns out they are nothing but the equations of a circle. And since they're the equation of a circle, actually we can get a graphical solution to solve for the principal stresses out of this block. And this is his version of it. Nothing wrong with that, but there's not much room for me to write on it because it's pretty much already fixed. Let me show you on a blank piece of paper how to plot this Moore circle. First off, let's move that entirely for right now. You draw a set of axes. You know to do that from the picture. You'll know to label this one the sigma axis because in the book it shows you it's the sigma axis. You'll know to label this one the tau axis because it's in the book. Now the first thing you do is you plot these stresses right here. Any one of them you want, it really doesn't matter. You have to use the sign convention listed in your book. Tension sigmas are positive, so this is a positive number.
So I go 1, 2, 3 divisions to the right. Then the tau value is 7. So now I got to find out the sign. Shear stresses are positive when the pair acting on the opposite and parallel faces form a clockwise. Well, look at these guys. This guy right here is a clockwise, and therefore he is a positive to be plotted. And so I go 1, 2, 3, 4, 5, 6, 7. That represents the stress on the vertical face. The vertical face stress has been plotted. It's got a sigma positive 3 and a tau positive 7. If you were to plot this one instead, you get the same thing, because that's a plus 3, and that's a clockwise moment due to this guy. So you plot 3, 7. Whichever vertical face you plot, they're the same. Now let's plot this thing here. This is a sigma-wise 5 compression. The sign convention says tension is plus, so this is a minus 5. So I come over to my diagram and I go 1, 2, 3, 4, 5 down the sigma axis in the negative direction. And then I plot this 7. Well, the 7 shearing stresses are positive when the pair forms a clockwise. Well, this guy doesn't go clockwise. This guy goes counterclockwise. So he is a negative 5, negative 7. So I go negative 5, minus 1, 2, 3, 4, 5, 6, 7. Now what that is that's 2 points on a circle, the circle of which is defined by those stress equations we had earlier. And since that's 2 points on a circle, all I got to do is draw a straight line, and that's the diameter of a circle. And therefore this is the center of a circle. And if that's true, then I can tell you how long the radius of this circle is. This radius is, got a number there for me? 1, 2, 3, 4 squared, plus the following number squared, 1, 2, 3, 4, 5, 6, 7 squared, and then you take a square root. I mean, I just pick it right off my graph. How big?
8.06.
8.06 KSI big. Now, I can plot a circle with a radius 8.06. Here's where it goes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's 8.06. This circle goes through that point. I can plot it right below this point. 1, 2, 3, 4, 5, 6, 7, 8.06. This circle goes through that point. I can plot it above here. 1, 2, 3, 4, 5, 6, 7, 8.06. I can plot it to the left. 1, 2, 3, 4, 5, 6, 7, 8.06. Goes through that point. Goes through that point. That's Mr. Moore's circle. The interesting thing is, this is everything you had in those equations. That means that sigma principal 1, usually consider the one to the right, is how far to the right? 1, 2, 3, 4, 5, 6, 7.08. You just measure it. That is the biggest tension stress, since it's on the tension side of the circle. That's the biggest tension side that lives inside of this block. You'll notice you had no idea there was a 7, because you only had 5 and 3. That's why you need these principal stresses to find the biggest stress. The biggest compressive stress, this is the compression side, is, you don't measure from the center of Moore circle, you measure from the axis. 1, 2, 3, 4, 5, 6, 7, 8.
fishy here. I'm supposed to add, well, I don't know, it's a pretty bad circle. But I'm supposed to add a radius plus 1. So it's got to be 9.06 whether I plotted it right or not. Sigma principal 2 is 9.06 KSI compression. Tau max, nifty. Tau max is the radius of Moore's circle. That's how high it goes. These circles always center about the x-axis. Tau max is 8.06 KSI. Now, let me tell you one more thing. I'm not going to tell you why, but you do need to remember it. If you ever plot a Moore circle that looks like this, that's really the stress in the plane that you're drawing. This is sigma P max, this is sigma P min, this is tau max. The truth is, if you come out of the plane of the blackboard, there's another circle that goes right in there, and another circle that goes right in there. Nobody cares about them because they have the same maximum compression, they have the same maximum tension, and the tau number isn't any bigger than ours, so nobody cares. However, sometimes when you plot your Moore circle is all on one side. It's always centered. This is sigma P1. This is sigma P2. And this is tau max. Except there are two more circles just like this one. There's another circle that goes back to 0. Nobody cares about that circle because it has the same maximum tension, doesn't have any compression, so we don't care about it, and its tau value is smaller than our tau max, so nobody cares about that circle. This is the one that kills people. There's another one that you don't see out of the plane of the drawing. You don't much care about it. It has the same principal tension, has the same principal compression. Its problem is tau max is sigma P1 over 2, and you weren't predicting that much. That's higher. So that's one trick you got to watch out for when you plot Moore circle, when you draw your stresses. If the circle is all the way to the right, then tau max will be half of this number. If the circle's all the way to the left, tau max will be half of this number. So watch out for that. Blow and go here. There's a couple of things that are probably important enough you really are likely to see it, so it's probably worth another 10 minutes. Many times you'll have a bar, the guy did nothing but stretch it in tension. First off, people always think that if you put a pure tensile force on the bar, then you cause a pure tension sigma P over A in the bar. And you do cause that stress. But if you would cut the thing at a 45-degree angle, you would see that at 45 degrees there is a sliding stress in there also. So just because you have pure tension, don't say 0 for how much shear is in the bar. There is some. Proof, here's the little postage stamp. Here's the P over A on both sides. There's none this way because nobody's pulling it this way. You plot your Moore circle, you plot P over A and no shear. There's P over A and no up and down on the axis. Here you plot no P over A and no shear. There's no P over A and no shear. You draw a Moore circle, look at that. That tau has a value. It's actually half of the P over A stress. So be careful. The trick for all profs, perhaps the exam, will say, how much shear is in a bar? When the guy didn't shear it, he just put pure tension. There is some. Now, let me give you a couple of cheats. I don't know whether it'll get quite this complex or not. If you took the ME or the CE discipline specific, this is very likely to appear on there, but on the general, I don't know. If you have a load on a bar where both ends are locked off, and that's the only bar, then let me just tell you, that P, some of it comes here and some of it goes there. In order to find the load in here, you can't use statics, because you don't know what this is, P on the left, and you don't know how much that is, P on the right, and you can sum moments and some horizontal forces and vertical forces till you're blue in the face, and it keeps saying, I don't know, I don't know, I don't know. Let me tell you how big they are. Take the load and just pretend it's on a regular simply supported beam and find the reactions. That's how much is on the ends. There's, of course, a reason for that. It's because of compatible deformations, but it's very handy to know if this is 6 feet and this is 12 feet and this is 3,000. It's really nice to know that you can just put 3,000 pounds on a simply supported beam, make that 6 feet, make that 12 feet, and solve for that reaction. 3 times 6 divided by 18, and the answer over here is 1,000 pounds. Bingo. And if that's 1,000, this is 2,000. You'll notice I changed the percentages from 0.3 to 6 and 12. Interestingly enough, torsion works the same way. In both these cases, the bar has to be the same size. I can't imagine them giving you more than one size bar. It has to be made out of one material. I can't imagine them giving you more than one material. But that's a restriction. If you put that torque on there, and it is at this position on the bar, just put it on a simply supported beam, call it T, and solve for the reactions. That's how much resisting torque will go to each end. 0.3 of the torque, 0.7 of the torque. You'll notice as the torque gets down towards the left end, this number gets bigger. When the torque is jammed up against the end, the torque will be torque. It'll all go into this wall, none will go down there. We already discussed this. I'm going to let this go. It's on page 69. Look back at the first. You have a bar of length L, has a gap. If the bar gets hot, it gets longer. It's your job to get a hydraulic jack and mash it back to the beginning. You should be able to do that from what we talked about earlier. If they give you one where you have steel bars inside of concrete, or perhaps you have a molybdenum bar with an aluminum bar, two different materials, when you mash on something where all the materials are all one thing, it has to go down delta, and since they are locked together, the deflection of the concrete has to equal the deflection of the steel. If you look back in your notes, you'll see you have an equation for concrete deflection, PL over AE. It's equal to the deflection of the steel, PL over AE, subscriptum with C's and S's. Your second equation is that the total load applied is the sum of the two loads that drops into the concrete and the load that drops in the steel. This is how much of the total goes into the concrete. This is how much of the total goes into the steel. Gives you two equations and two unknowns. Finally, if you look on page 33 in the manual, if they give you a beam that's a cantilever beam, you can solve for everything in that cantilever beam. If he props the end up on the end with an unknown force, statics alone won't do the job. Take that off, let the beam deflect like it wants to, even though the boss will really be hacked, because he didn't want it to deflect on that end, and solve for this number from page 33. Then go get a hydraulic jack and push this beam up
such that this movement up is exactly equal to this known number down, you'll find out how big the hydraulic jack has to push to make this original case happen. This equals superposition of this plus this. All right, we're already 40 minutes over. You're still there. If I'm still talking to anybody, you're very patient and you want to pass very badly. The rewards of being a professional engineer are tremendous. So, believe me, you want to pass very badly. The chances are you will too. If you come to these sessions, you probably are interested enough to study the amount of material necessary to do so. If you have any questions, you can call us or you can email us. I'll see you Wednesday night to discuss the previous session we had, namely statics. Then I'll probably see you again the next Wednesday night to discuss this material. It doesn't much matter which one. Probably if you want to come this coming Wednesday and do them both, that's all right too. We wish you all the luck in the world. If we can be of any help, give us a holler. We'll see you.